All right, let's go ahead and get started. So happy Monday. And so I did grade the stuff that I got, so you can look at Blackboard and check that out. And I finally fixed Blackboard for my in-person class, so that's all nice and updated. The grade book is probably still all screwy. That's just the nature of Blackboard, but I'll try to get that fixed so that it's actually accurate. And then, so something that we need to think about for the in-person folks. So looking at our calendar, so I don't know if you can tell, I'm pregnant. So unfortunately, that means, because my OB is leaving, so I think I have to have my baby this week, which is finals week. So then something to think about, and y'all don't have to answer me this second, is would you want to take either the online final, so I'll probably, I'll still be by email, I just can't like physically come in on that last week. So you could either take the online final that I have, that I give to my online students, or the other option would be like to take the final the week earlier, maybe do like a take-home final instead, and have it be due on week 10 or something. So those are kind of the two options. So we could talk about that kind of in lab, what as a class you decide, or kind of what people are feeling, but just kind of think about that. So I'm just trying to plan early so y'all won't be surprised at the end. And then online, just again, make sure you get the assignments. So we'll turn in the homework. Then I have the lab to give back to you. You see that I grade pretty leniently. And then make sure you get this week's lab. So we'll be doing that on Wednesday. Good practice on sig figs, especially for the pre-lab. So definitely check that out. All right, so let's get into it. So now we're just going to start kind of poking through the periodic table and looking at the different trends again and kind of what are elements. And so like we said, a pure element was just a substance that cannot be broken down. And this is where we have, right, our periodic table of elements. Just kind of, right, some fun facts. So of course, right, we have, I believe it's past 88 is synthetic. So we have, right, a lot of synthetic elements. So they try to make new elements, right, by colliding particles together. And so yes, our periodic table looks kind of nice and complete. But note, right, like in theory, we could add new elements. So they're trying to discover right now 119 and 120. I think currently they're saying the Japanese researchers are leading the way, but we'll see who actually smashes the particles. And then of course, right, you have to detect them long enough. And most of these have pretty small half-lives, which we'll kind of talk about, but not really. So we have our periodic table. And then of course we should just at least be somewhat familiar with what elements are in the human body. So this is just kind of highlighted in your textbook. And obviously, right, we're carbon-based life forms, and organic molecules tend to have this general formula of carbons, hydrogens, and oxygens. And so as you might imagine, right, we're primarily carbon, hydrogen, and oxygen. This is by mass. Obviously a lot of oxygen. And then, right, we also have nitrogen. So nitrogen is also part of a lot of organic structures. And then we're going to have our essential minerals. Well, these are obviously, right, our big ones. So calcium, essential for bones, and phosphorus. And then, right, then you start getting into all your other ions, which are important. So potassium, sulfur, sodium, chlorine, magnesium, right? All important. So we need our electrolytes. And so why do we need electrolytes in our body? What's it good for? How does your arm move? Well, right, so the sodium channels are a part of it, but right, it's all about you have to send an electrical impulse out to your arm. Well, how does electricity move? Well, you have to have electrolytes. And so, right, getting into different ions, sodium channels, all those good things, right? All those ions make your system move. You got to have electrolytes to get your muscle functions exactly. And so that's why they say, right, if you have some muscle cramps potentially, you should eat a banana. Maybe you're magnesium deficient or potassium deficient. So that's part of that. There's also like this whole new, I don't know if you guys have seen ads for like all those like LMNT and other like electrolyte drinks now that they're selling. And there's some science behind that, right? Because they're trying to say, well, we do need electrolytes, again, obviously for our body to function. So maybe pure water isn't as good as having some of these electrolytes. But that's kind of down the rabbit hole. But that does get into why you shouldn't drink distilled water, because obviously distilled water is the absence of ions, so you don't want to completely leach out your body. But water, just pure water is not really pure water. Anyways. So then we have compounds. And so the other thing we're just trying to take away now from this slide is how do we draw these symbols? And so, of course, let's just redefine compounds for a second. So we had said that they were two or more elements, so again, right, found on our periodic table. And then they're in some sort of defined chemical formula. And so we can have these discrete molecules, and then we'll kind of play with these kits, the Molly-Mod kits in lab. And so you'll find that the different colors also correspond to different elements. And so here, red tends to represent oxygen. And then we'll kind of see that again once you play with it. And it has two holes, which means it's going to make two bonds, which will kind of come back to this idea because we need to get into Lewis dot structure. And then we have the white ones here. So these white balls are always hydrogen. Black is carbon here. And some other colors, so we don't have them shown, but let's write out a few other ones. So green tends to be your halogens. So halogens are going to be fluorine, chlorine, bromine, iodine. I just wrote them as single. Remember, these are normally diatomic if we're talking about elemental halogens. Blue is nitrogen, and then yellow tends to be sulfur. And then, of course, we can have other colors for other atoms. And then again, we're just kind of appreciating what is this saying when chemists communicate with these drawings and symbols. And okay, so we can translate this. And then the whole point of this too is this is a space filling model. So it's trying to show geometry. So we can tell we have an oxygen here. And now I'm going to draw single lines. So representing two electrons. So And each one is contributing 1 electron, but we'll get into that kind of detail once we get into covalent compounds. Again, I'm going to add that there's 2 lone pairs, but again, we're not quite there yet. We're just, again, appreciating the structure for now, this sort of bent geometry. And so then this is just another kind of ball and stick model. Again, what's being shown, carbon, carbon. And then carbon, we'll learn, likes to make 4 bonds. Again, part of why we're carbon-based life forms. And also carbon is small, so that helps it form these bonds. So that's just the translation of that structure. And then, so the other way to draw this ethane here is just by a stick. And so this is the same thing. So this is still ethane. And so this is the most shorthand abbreviated. We probably won't see too much of that in here, but you still should be aware. And so with this, each endpoint is a carbon. So we have 2 carbons. And then the hydrogens you have to fill in, again, knowing that carbon makes 4 bonds. And so now looking at this structure, we want to be able to kind of translate it. Oops, sorry. Just trying to make another copy. And so what we want to point out is, again, every point here is a carbon. So this is a carbon, 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 and then it has to have 3 hydrogens. Carbon with 3 hydrogens to make 4 bonds. Carbon here, carbon, and then again, let's make sure that we're not missing any hydrogens because I didn't fill one in here. So we have carbon, again, 1, 2, 3, 4 bonds, so no hydrogens there. Carbon there, 1, 2, 3, 4 bonds, so no hydrogens. I already filled in that one. So it had 1 bond to nitrogen. That's why it had 3 hydrogens. Carbon there, again, 1, 2, 3, 4 bonds. No hydrogen needed. 1, 2, 3 bonds. So I need to draw a hydrogen on this one here. Then another methyl group. So again, carbon, 1 bond, 1, 2, 3. Another carbon here, 1, 2, 3, 4, so no hydrogens needed. And so then I might just redraw this for my sanity's sake. So sometimes, again, once you go into perhaps OChem or continue taking chem in the future, you might do something like this. So I already know where all my carbons are, so I don't have to explicitly say them, but then you always want to fill in the hydrogen. So that's the tricky thing about these organic structures. So let's write that. So the organic structures do not show hydrogen explicitly, must fill in on carbon. And it's only on carbon that they're missing. Let's look at another example. So if we just look up isopropanol, for example, if I can spell it. So isopropanol, let me just copy this. Oh, one more time. So we have isopropanol, and it looks like this. And so again, if you have a hydrogen attached to another element that's not carbon, so oxygen, nitrogen, you know, whatever, they are going to show it. So here it is shown. But then again on the carbon, so we have a carbon here, 1, 2, 3. So, okay, we need a hydrogen there. And then same thing, carbon. So these are, again, terminal methyls is what they're called. And so we need carbon with 4 bonds. So it looks something like that, drawn more explicitly. So let's practice. So this is kind of a funny one. See if you could come up with the formula for this one. And so for this one, I'd probably kind of redraw it for now, maybe more explicitly. And so again, right, each point is a carbon, and then we have to fill in our hydrogens. And so just examining how it's drawn, right, all the carbons only display 2 bonds, so we know we must be missing 2 hydrogens on every carbon. And then we can just add up, right, the total amount. So how many carbons do we have in this formula? 4, excellent. And then how many hydrogens? 8. Oh, 8 there, excellent. Questions on this simple one? Kind of funny looking. Okay, let's try another one. So just see if you can give me the formula for this one. Again, right? Fill in your hydrogens first, maybe rewrite it. Don't forget, right, all your little carbons here. This could be tricky. So I'll just start kind of filling in the hydrogens to start off with. And so note, right, this one has 1, 2, 3, 4 bonds. So, okay, that one doesn't need a hydrogen. All the others did. This one needed 2. Don't forget about this one. This is tricky. These like little isopropyl carbons. So 1, 2, 3. Again, note how the hydrogens are going to be drawn on the amine explicitly. And then, of course, this little methyl group here. All right, so what do we get for our formula then? So how many carbons?
9.
So 9, did we all get 9? Yes, no?
Yeah.
So yes. And then how many hydrogens? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, but then don't forget, so 11, 12, 13. Is that what other people got? Fixing, see, chat got that. And then our last one, so CH, and then nitrogen is our only element left. And so usually in order you do carbon, hydrogen, oxygens if there's oxygens, and then the rest of the elements kind of tend to go in alphabetical order, but that's not always a hard and fast rule, so we'll see a lot of other cases of polyatomics and other groupings, but we'll get there. All right, does this feel okay, how to interpret these? Roughly. Anybody know what this molecule is by any chance? So this is amphetamine. And then if you wanted to make methamphetamine, this would be a pretty easy precursor, so that's why it's always where do you start with. But you just methylate this nitrogen here, which is pretty easy for any chemist to do. And then you've made methamphetamine, and then right, that little methyl group just makes it more easy to cross that blood-brain barrier, so it allows for lower dosage. Obviously that's, well, that gets into more rabbit holes of what's a drug and what's a illegal drug, which isn't always clear, chemically speaking. Anyways, so now let's get into our atomic structure of our elements. And so again, we can kind of flip back and forth to our periodic table in thinking about this. And so now let's understand what dictates an atom's identity. So of course we have protons, neutrons, and electrons. These are all parts of our atoms. And so protons and neutrons make up our core, our nucleus here. And then electrons float around on kind of the outside. And then it's important to know, so we don't get too into it in this class, kind of the history and the details, but you should still be aware that, right, the atom is mainly kind of empty space. You have your core, again, your nucleus in the center, that's your protons and your neutrons. That's also where all your mass comes from. And then it's mainly kind of empty space. So atom, mainly empty space. And if we go historically, this goes back to that gold experiment where they threw alpha particles at gold and they found that most of them just passed straight through because, again, it's empty space. And when they did bounce back, they bounced back directly at them. So again, showing that they're hitting that nucleus in the center. And then your electrons, again, they kind of float around on the outside, and we'll get into it a little bit deeper than maybe you've gone into it in some of your other classes. So trying to understand where the electron is exactly. And so again, we mentioned that our protons and our neutrons, so they're where our mass also comes from. And they have nearly identical masses. And so these are the exact masses, but what's more important to note is they're both about 1 AMU, so atomic mass unit, and we'll get to what this means. And then the mass of the electron, so if you compare the order of magnitude, so negative 27 kilograms versus negative 31 kilograms. And so that's why we say this mass is negligible. Oh, if I could again spell. And so of course, even though the electron does not have a mass, it is still important. And so we have here that the charge of the proton and the charge of the electron are equal in magnitude, but opposite in sign. And then neutron, kind of you can tell by the name, has no charge. And so formally, the proton is assigned a positive charge. The electron is formally assigned as negative. And so this is kind of the good cheat sheet summary. Again, right, we're just paying attention to the mass, that the proton and the neutron are basically 1 AMU, our electron is 0, and then again the charges. And so here's a Coulombic charge. Again, I don't think it'll be too relevant in this class. You could explore how it was derived for the Millikan oil drop experiment. Kind of cool how they did that. But otherwise, just know a proton has a +1 charge and electron -1 charge. And so again, right, just flag me down for questions, especially if I'm going too fast. And so then we start to get into it. Okay, well, elements are defined by their number of protons. And so again, right, whatever you need to do, star this, change this. So if you change the number of protons, right, you change the atom. So again, just keep that in mind. And so this is really useful. So, right, again, take a look at your periodic table. Most of you have them out. That's great. So we have these numbers in our upper left corner. So again, that corresponds to our atomic number, which is our proton. So, right, if you want to put that on your key, oh, okay, just my atomic numbers equals my proton. So you don't forget it. Right, so this is your cheat sheet here. So we have 1 proton for hydrogen, right, 2 protons for helium, and right, they just go in order. So 3 protons, 4 protons for beryllium. Okay, so now we know how to get that element. And so sometimes you might also see this referred to as its atomic number and Z. So again, that's just a definition. And so now kind of looking, let's look at some of our, so let's look at isotopes now. And so let's look at kind of what they are. So let's start with this helium nucleus here in this little picture. And so again, now it's showing us our nucleus, and we have our 2 protons indicated by red color. And then it's also showing us, right, these 2 blue balls, so that corresponds to our neutrons. So 2 protons, 2 neutrons. And so now we can get into kind of these atomic symbols as well. So if we're looking at helium here, so then we could write it as 4 to helium. So this is just our atomic symbol here. And so this is our total mass, which is just neutrons plus protons. So that gave me 4 here. And then 2 corresponds to, again, our protons or our atomic number Z. Again, right, same thing. And then I just have my little helium symbol, which should match this number, right? So it's kind of redundant, but also a good check that, like, oh yes, this is 2 and that is helium, right? And then you just go back to your periodic table. 2, helium. Okay, they should always match there. And then let's look at carbon. So carbon, so this is the most common isotope shown, which we're about to get into what are isotopes. And so again, we have 6 protons here. So 1, 2, 3, 4, 5, 6 red balls, and then 1, 2, 3, 4, 5, 6 blue balls. And so, right, we can tell we have 6 neutrons, 6 protons. So that gives us a total mass of 12 AMUs for this carbon. So we're looking at carbon 12 here. All right, so now let's get into it. So we'll look at this column thing in a second as we kind of tour the periodic table, I'll say. And so we're kind of seeing, well, elements are obviously arranged by their atomic number, but then what we're kind of getting at is they're in these columns, so that's why we have hydrogen on one side, helium all the way over there, then we're back to 3, 4, weird gap, right, 5, 6, 7. And so again, they're grouped by their similar properties. So similar physical and chemical properties. So again, we'll look at that. And the goal is to kind of start tying all these properties together with its electronic structure. All right, so then blah, blah, blah. We have our chemical symbol. Usually there's a name. And so let's keep going. So what are isotopes? So isotopes are just defined as elements with different numbers of neutrons. And so, right, this is just kind of a phenomenon. Scientists aren't really sure exactly like why these isotopes form, but basically, right, we know when they come together, they can come together in different kind of ratios. So let's look at, so they're giving neon, but I'd rather talk about carbon for a second, right? So we have carbon 12, carbon 13, and carbon 14. And so again, right, they all have 6 protons, but now just different neutrons. And so let's go through that. So let's do protons, neutrons. So how many neutrons does carbon 12 have? 6. And then, so how many neutrons does carbon 13 have? 6 protons. And then how many neutrons does carbon 14 have? 8. Excellent. So good. So we want to be able to figure that out. But then there's some other connections that we should make here. So let's look at, where does this come from? And so kind of, let's look at our periodic table and look at some things about it. And so again, this is why I want to focus on carbon for a second. So if you look at carbon on here, it has this mass here. But what's important to know about this mass is this is the average atomic mass. So it has here atomic mass, right? But it's really the average mass of our isotopes. And so what I mean by that, and we can do it kind of roughly. I have to look up the isotopic abundances. Actually, it's not too relevant. So we can estimate it. So carbon-12 is the most abundant. It's approximately like 99%. So again, right, most of it is going to be carbon-12. And then carbon-13 is that last 1%. And then carbon-14 is obviously less than 1%. And does anybody know what's significant about carbon-14? And probably why it's also low. So this starts to get into like kind of the why, or you can start to think about the mysteries of life. But basically what you find, especially on the lower elements, is once you have this like mismatch, I call it, then it kind of tends to become unstable, right? So again, we said that it has 6 protons, 8 neutrons, and so it has more neutrons, and because of that, it's a little unstable, so it is radioactive, carbon-14. And so again, right, scientists aren't entirely sure why certain ratios or combinations are radioactive. That's just part of it. It's some sort of instability in the nucleus. But again, you could get into that, right? Just you have to look up each individual isotope and see kind of, is it radioactive? But then once we want to get our average atomic mass, like on our periodic table, what you'll do is you'll take your mass of each one. And again, I'm kind of doing a little bit of rounding. So if you were to do this exactly, you would take way more sig figs, blah, blah, blah. But I just want to roughly take 12 AMU times our percent abundance, so whatever percent abundance you're given. So times 0.99 plus 13, again, AMU roughly, times 1%, so 0.01. And just watch that. This will come up on a lab later. You'll do these percent abundances. And then, sorry, let me get my calculator out. And so then we can kind of, again, roughly see how we got the number on the periodic table. So 12 times 0.99 plus 13 times 0.01. And so, right, again, since I'm using pretty rough numbers, we get 12.01. But now that's hinting, yes, that's why we have a little bit higher than 12, right? So most carbons all have a mass of 12, but then that 011 is from obviously other isotopes. And so that being said, right, if you're like given these problems, because you're given like these homework exercises, and so if you're not given, right, the protons plus the neutrons, so that's again always the best way to get the mass, because you're always talking about, right, a certain isotope. But if it doesn't give you this hint, then you can just kind of round right to the nearest whole number for an isotope. At least that's an okay guesstimate. And then I do want to point out a scenario with bromine, because bromine here is one of those where if you take our average here, so we get about 80, but there is no bromine 80, and so bromine's kind of fun. And so if we do bromine, bromine is funny because it has 2 isotopes in about 50% abundance. So we have bromine 79 and bromine 81. And like I said, they're about 50-50. And so again, right, if we were to do the math on that, we can see the average is about 80. So that's why our mass on our periodic table is about 80, But again, right, there's not one isotope of bromine that is 80. It is half of them are 79, half are 81. This is just the average of those abundances. And so again, all these, right, are averages. And so for most of your exercises, you're finding, again, your mass by adding your protons plus your neutrons. So then let's practice that for bromine, 79. So how many protons and neutrons do these species have? So check your periodic table. So how many protons do both of these isotopes have? So 35. So excellent. So again, just so we're all on the same page, right? We look at our periodic table, 35 there, okay. And so then, how many neutrons do we have for 79? So 44. And again, right, we can do the subtraction. And then how many neutrons do we have for bromine 81? So 46 there. Questions on that part? People will copy that. And then, so if we go back, all it was saying is, again, right, we have these three different neon isotopes, 20, 21, 22. They're all written with their atomic symbol. Again, they all have 10 protons, right? They're all neon. They just have different masses with our different neutrons. And of course, it points out they either have 10, 11, or 12. And then the other thing to just kind of note is a different representation. So of course, this is the most comprehensive, right? We have the most information, our mass number, our atomic number, and our symbol. And again, right, don't forget that our mass is protons plus neutrons. So just reminding us again. We may also see it in other forms, so I'll just make sure. You could also just kind of see it more written like so, neon 20 are kind of like I was doing, right? I was just doing 13C, so they may not put the proton number. All right, so see if you can write out the symbol for a chlorine isotope with 18 neutrons. So what would that look like? All right, so what is our symbol look like? So what's like the letter for chlorine? So Cl. And then, again, just to make sure that we're clear, notice that always the first letter is capital, the second one is lowercase, if there is a second letter. So again, just kind of take that in, right? Magnesium, capital M, a G here, chlorine, obviously, capital C, lowercase l, like we just saw. Some of them only have one letter. And then, so what's our mass number? Or maybe I should ask, how many protons does chlorine have? So 17. Again, right, we can get that from our periodic table, 17 there. I'll put that on the bottom. And then what's our total mass then if it has 18 neutrons? So 35 there. And so, right, we can just do 17 plus 18 since it said 18 neutrons. So chlorine, 35. Questions about our isotopes? Okay, this might be a good spot for our break. So let's just take a 10-minute break or so, be back around 2, and then we'll continue with ions. All right, I think we all made it back. So let's continue. And so now let's look at ions. And so now these we can define as atoms with different charges. And then you're either going to gain or lose electrons. And so let's kind of think about that and probably back up for a second to our neutral form here. So we can even look at chlorine 35 here. So we have chlorine 35, and so what this is implying, the way it's written, so written as neutral. And so that means that our protons equals our electrons, right? And so the other way I like to think about this is I like to say that our charge is equal to protons plus electrons. And again, right, you're keeping in mind that electrons are negative. So if you like to say protons minus electrons, that works. In my brain, again, I've already made electrons negative, so I'm already adding a negative. So in our neutral case, how many electrons do we have? So look back, right? How many protons does it have? No charge. So it has to equal electrons. So how many is that? Oh, check, because remember 35 was the atomic number.
Oh, 17.
So 17. So 17 electrons. And so now let's look at an ion. And so again, right now we're just kind of looking at the formal definition, but then as we keep going through the course, right, we're going to see what ions it tends to be and kind of the why behind this. And so now let's just practice. So what if we have 35 chlorine now with a negative charge? And it could be written in different ways, right? You might just have a negative there, or, you know, they might bother to write out -1 actually. And then obviously if it's greater than -1, or then it's going to have other numbers. So that will be written. So then how many electrons are in chlorine 35 with a negative charge on it?
18.
So 18 electrons. And again, right, there's several different ways to think about it. You could start at the neutral and see, well, I have a negative charge, so we had to have added, right, electrons. You could do the formula, like I say, so -1 is equal to protons plus electrons. I know I had 17 protons, and then I have to have, right, 18 electrons to get to -1 there. So let's try another one. So what if we have, let's do 36 sulfur 2-. So for this one, give me protons, neutrons, and electrons. Just take a minute for that. So let's start with, so how many protons do we have? So 16, and again, just for explicit sake, okay, we got that from our periodic table, right? Sulfur 16, excellent. And then how many neutrons? So 20, so again, 36 minus 16 then. So excellent, 20 neutrons there. And then how many electrons? We have a -2 charge. Yeah. So remember, compared to the protons, so yeah, it should be 18. Good. Questions on this one here? So let's do another one. So let's see, 48 titanium with a 3+ charge on it. So same thing, just protons, neutrons, electrons. All right, let's hear how this one went. So how many protons do we have? So 22. How many neutrons then? So 26. And then how many electrons? 19. Sound good to everybody? Questions on this one? You can ask questions, right? I don't know if I'm going too fast unless y'all like wave at me and ask questions, otherwise I'll get excited anyways. All right, so let's keep looking at our chapter then if we feel okay with this. And so again, we're kind of just wanting to put things together and start familiarizing ourselves with our periodic table, right, and our elements. And so let's kind of look at our structure and again our table here. And so again, I like this website. Whether you're in person, online, it's an excellent resource just because I like how it works. And so we can start over here. So this is our group 1. And then obviously hydrogen is the exception here. And so again, just kind of orient yourself with every periodic table. It's going to be a little different. You have that one in the back too. Also a little different, different information. For example, that one has the states of matter based upon like the colors. This one, right, obviously they're highlighted. So here's our key. So our blue, right, signifying our nonmetals here. So there's hydrogen. And then it is the one little exception. So it is a gas, while the rest of these would be known as our alkali metals. And so what do we know about the alkali metals? Do we know anything? Yeah, they're really reactive. So I'll probably demo it on Wednesday. So we do have in lab lithium, sodium, and potassium. Potassium was by my request. So let's look. And so why I like this too is, again, right, Wikipedia can be our great resource for science. I thought this used to function a little bit better, where I could see the picture without having to click Wikipedia. And so you'll see this on Wednesday in lab, but again, characteristic of the alkali metals are pretty soft, and you can see that here. So what you can't really appreciate from this picture, well, it's not really clear. So we're not sure what atmosphere this is in. So notice, right, it does make the note that it is freshly cut. Again, we can examine this in lab. But basically, again, right, we said they were pretty reactive. And so even lithium, right, it's going to be reacting with the water in the air, and then so forming what's called these oxides. And so it just looks like white, I call it white poop stuff. Again, we'll look at that in lab, so you can kind of tell the integrity, right, of your samples. I won't show videos of things exploding because, like I said, we'll do that in lab. As we go down, so they get softer. So sodium is, again, soft. This is obviously in an inert atmosphere. Potassium is the last one you can work with in air. And this one does have the, what's it called? A chance of igniting in air when you slice it. And yes, I have had that happen to me personally, and it makes a nice purple flame when you slice it, if it's nice and fresh. And so again, most of these are stored under parafilm oil. So again, you'll see that once I bring them out to play with in lab. So they're all stored under mineral water, and they all react with water to generate hydrogen. And so that's something that we could kind of write. This is maybe a little ahead of the course, but that's kind of the nature of like chemistry and trying to learn it all, especially when you're like in the beginning, right? It's like a lot of things to understand. And so we can at least look at the types of reactions. So we have lithium plus water. And so all of these, so this is going to be alkali metals plus water reaction. And so they all react in a similar manner to make a hydroxide. So whatever metal hydroxide, this is a base, which then we can see by the use of an indicator. So I'll bring that in lab. And then the secondary danger, which again, maybe we'll see this in lab, is the other thing that you make is hydrogen gas. And so this can cause for extra explosions and issues because, again, safety considerations to think about. And again, you'll see this firsthand. But you have your little bit of metal here. It's kind of floating around your water. But as it's decomposing, right, it's making hydrogen gas, which is also flammable. So that has the extra tendency to kind of, light off as well. So if you have a kind of tight headspace, this can get a little explosive, which, yeah.
How come we have 3 hydrogens in our product?
I just didn't balance the equation.
Oh, okay.
So yeah, I just showed you kind of this unbalanced equation right now, right? So then we'd have to go through balance it properly. So probably 2, 2. Does that work out? Does that work out? So 4 hydrogens, 4 hydrogens. 2 oxygen. So now it's a balanced equation. So yes, I just didn't give it to you balanced. And that's something that we'll get into, right, as we progress the course of like balancing the equation. But right now the takeaway was just we make a basic salt and more explosive flammable hydrogen. Yay. And so afterwards, so after potassium, then they get way too reactive to work with in air, so you are unable to work with these. And so you can tell that, right, rubidium is in this sealed ampule, and you would only work with it in a glove box. I've never worked with rubidium, personally speaking. Cesium, you can watch videos on this on YouTube if you get bored, right, of people busting open these cesium ampules, and they are obviously crazy explosive, pyrophoric. And then francium, you don't want to play with, so it is radioactive, so can't play with francium there. All right, so then that takes us to our alkaline earth metals. And so again, this periodic table breaks it up very explicitly. Oh, the other thing, well, we'll get into that later. And so again, still metals in character. So let's look at beryllium. And so again, right, still metally looking. The distinction is now our alkaline metals, or alkaline earth. They're basically not as reactive as our alkali metals. So that means they can potentially react with water more slowly. If they do react, so we see that with like calcium. So calcium's pretty slow to react with water. I'm not sure if magnesium even reacts with water on like an appreciable time scale. And so some of these require what I call the use of acid. And so we will do that. So they tend to react with acids then. So we'll see that like with HCl. And we'll do a lot of magnesium dissolving in this class. So basically just taking a little strip of magnesium, reacting it with hydrochloric acid, and then we'll make magnesium chloride, and then we'll make hydrogen again. So, right, kind of similar in some ways. So, we're still making hydrogen, right? So, releasing an explosive gas potentially, or flammable gas. But then it'll dissolve. So, reactivity. And then, so we're going to kind of skip the transition metals for now. This is actually my favorite part of the periodic table, but we just don't want to get too much into it. There's a lot of reasons why they behave, we'll just say weirdly for now, but basically they also make pretty colors. So, right, like a lot of these can be used in fireworks and make colors. So like nickel tends to be green. Cobalt can be a lot of pretty colors of like blue and purple. Iron obviously tends to be like red. Manganese can be like yellow to purple. Same thing with chromium. So all these, right, have specialized uses. We can also at least just point out, right, we have our coinage metals. These are fondly known as, right, copper, silver, gold. So people have obviously prescribed a lot of inherent value to them. A lot of that has to do with the rarity, obviously, of these metals. We have over here what I would call our workhorse metals. So particularly palladium and platinum are used in a lot of catalysts. But like I said, we'll kind of ignore the transition metals in our course. And so then as we kind of start looking at this, so we go from metal character and then slowly going to non-metal as we go from right to left. And so if we look at this little key here, right, we have what's called our post-transition metals. And our group 3 here, so we could look at, so this is group 3. So boron, aluminum, gallium, indium. These are all pretty cool. And so notice, right, we just kind of skip over to 3. That's another way to identify them. So group 3, we'll also learn, right, 3 valence electrons, but we'll kind of come back to that. So group 3. So we have boron here. So notice boron, though, is part of the semimetals, right? It's on that stair step. And there it is on this key, right? Semimetals. So this is kind of our dividing line then between our post-late transition metals and then our completely non-metals over here. And let's just look at kind of our characteristics. So boron, again, right, still kind of a metalloid looking thing. Used in a lot of main group applications, different materials, right? Boron carbide is a new one. I don't know if anybody uses borax for laundry, but that's also a boron-containing compound. Boron also burns green, which is kind of fun. And then, so right back to our post-transition. So aluminum is right under boron. So again, right, that's soft. Obviously, you have aluminum foil. Gallium is always a fun one. So gallium, if I could click on it. Oh, come on. I want to look at gallium. So the fun thing about gallium is that it's a liquid at relatively room temperatures. So here it is, the melting point of gallium, so 85.57. So that means it's kind of fun because people like to hold it in their hand and it melts. There's also, I don't know if you've ever heard of the book, The Disappearing Spoon. That's like a trick in there, yeah, where they like put a gallium metal spoon in hot tea and then, oh, the spoon disappears. That's because of, again, gallium's super low melting point. Honestly, though, I found it a pain to work with metal gallium when you're like trying to hold it in your hand and like, please melt and break apart so I can weigh you. But that was not fun. And then indium. So again, right, metal looking. Thallium. So thallium, fun fact, is toxic. So as any like organothallium compounds. So thallium is kind of on my list of things I will not work with just because it's pretty toxic. That being said, I did work with it once and I didn't like it and then it didn't work, which I was happy about it. So I certainly did not want to do thallium. Thallium is also linked to like poisoning and hair loss over time if you were to have some sort of exposure. So, and then moving over, so group 4 then. So of course we have carbon at the top of group 4. And again, like I mentioned, we're carbon-based life forms. Why we're carbon-based life forms? So carbon is a little smaller than you would expect it to be, even by periodic trends. And so again, it makes single, double, triple bonds. And then people have tried to maybe make silicon-based life forms or try to make, compounds that are very analogous to carbon with silicon, but it just doesn't quite work out necessarily, but there's plenty of research in that area. And so of course carbon, so let's just go back and look at our pictures here. So carbon, is obviously this black powder, or like we mentioned, right, it has other allotropes. Oh, that's the other thing. So have you guys heard of like those trends of like black ice cream or black ice cream cones or stuff like that? And so if you're wondering what they use, most of the time they might use like a carbon powder to make it black. There's just one problem with that. So carbon can also be used as like a purifier. So basically, right, it sucks out potentially minerals from your body. Like some people swear it's like a detox thing. But that being said, right, especially if you were taking like medications or something and then you go have this black ice cream, it could make you feel ill, right, if that carbon again is sucking out either your medications or, you know, something else. Again, everybody's body is different, so that's just kind of a fun fact there. Otherwise, I guess you have to use like squid ink to get it black, but that might be too expensive. And then silicon. So again, it's this kind of metalloid semiconductor. So obviously silicon is used in a lot of chips. And again, like I mentioned, right, a lot of research for carbon analogs made of silicon. So germanium is again also of research interest because of that, since it's similar to carbon and silicon. So again, trying to make it do what carbon does. Tin is another toxic compound now, especially organotin toxic compounds. So tin metal is okay, but like I said, organotin are highly toxic. Same thing with lead. So lead is also toxic. Lead, though, is essential, though, for blocking radioactive isotopes. So we have a few radioactive isotopes at RCC for like learning purposes, and they do live in this what's called a lead pig. So it's just like a little container of lead so the isotopes don't escape. And so now we move over. So group 5, and they formally have this name of pictogens, which I always kind of mispronounce. And so we have nitrogen. And so I will bring in some nitrogen at some point for y'all. So I'll bring it in the form of liquid nitrogen. So you could see that and how that is. So that is fun. And so nitrogen is this clear liquid. And obviously, right, it turns into a gas. It's the majority of the air we breathe. Phosphorus. So again, we looked at phosphorus. And so again, these are non-metals at this point. So we had our different forms of phosphorus. Arsenic, so notice arsenic is back metalloid. So stair step again. And so again, right, toxic. A problem in the environment as well. Just kind of thinking about arsenic. So you don't want to get it in the water supply, again, for obvious reasons. So antimony, so again, another metalloid. And bismuth, so again, more metally. And so now we move over to group 6. So group 5. Group 6. And again, they have this special name, the chalcogens. And so oxygen, we probably know about, and oxygen, right, is essential. Excuse me, we breathe it. And so the fun thing about oxygen is it is blue. And I will condense it for y'all so you can see that, believe it for yourself. The only other thing, though, so liquid oxygen is pretty dangerous if you were to combine it with like an organic. And so this is cool to play and condense, right, in this like environment. But this is actually a huge safety hazard for like air-free chemists. And so basically, if you were to put oxygen with an organic, that would be a bomb. And so when chemists accidentally do this, you have to evacuate the building or your lab, and you just let the pump off the oxygen and hopefully not explode things. And so then I also like to refer to group 6 as our smelly group. So all these compounds are smelly, except for oxygen, of course. And so sulfur, and again, you'll kind of play with it. So pure sulfur itself is not smelly, but you will notice once we play with it in lab that probably a real sample is smelly because it is slowly decomposing and making hydrogen sulfide. And so that gives it a smell. And so again, all these things get pretty smelly. And for example, this compound thioacetone was pretty famous. So let's see what happened. So they tried to distill it, and so right, it mentions the smell is potent, and in 1889 they attempted to distill it, and they in this city, the whole city had vomiting, nausea, and unconsciousness within this 0.75 kilometer radius due to the smell. So super horrible. And you may be familiar with this without even knowing it. So they have their proper name here, methanethiol. You may have heard of it, mercaptan. You know what this is used for? They put it in a natural gas because otherwise natural gas doesn't smell like anything. So they put a little bit of mercaptan in there so you can tell if you have a gas leak. And you don't need very much at all. So your nose, I think, probably has parts per billion detection on these compounds. And so then the smelliness just continues. So selenium is, again, also known for making smelly compounds and can be toxic. So right, if you get overdosed, you have all these symptoms. I believe if you were to also ingest them, you would end up with some sort of selenium breath, which would be horrible. And so then it just continues on down with tellurium, again, with that toxicity, the smell. And so it does mention that people who, if you work with tellurium, right, especially over time, then you get what's reported as tellurium breath. And so notice, right, it's pretty small exposure limits. And if you start reading about it further and like people back in the day experimenting with chemicals, it mentions that people like apparently committed suicide because I guess like, if you get this tellurium in you, your breath is so horrible, like everybody hates you and shuns you because you smell now. And so yeah, safety first. But that is these smelly compounds. So yeah, they all have those horrible smells. And then, except for polonium, so I don't think polonium, although it is radioactive, so maybe that is why people haven't experienced polonium breath. I'm not too sure. But, and then obviously, right, they could also be toxic. I'm not sure of the metabolic pathway. I think it's been studied. But we can just think about, right, oxygen is obviously essential. And so that's kind of the problem with sulfur. Again, speaking from personal experience, right, if you get exposed to CS2, the problem with CS2 is that sulfur will bind to your iron heme a little bit stronger than oxygen, so it's then difficult for your body to get rid of the sulfur. So if you get exposed to CS2, it's kind of like being drunk, at least for mild exposure. And then moving on, so our last bit, so we have our halogens over here. So again, they're all pretty reactive. And so this is fluorine. So fluorine's a gas. Obviously, they've condensed it at a low temperature. Fluorine's difficult to work with, again, because it's highly toxic, reactive. I've seen other chemists do fluorine chemistry, and it's like horrible. You have to have a special regulator, and then fluorine is eventually going to eat that regulator, just like it eats everything. Chlorine is also pretty much just as nasty. Usually you can generate chlorine, though, like gas in an experiment, but not always the easiest thing to do. Bromine is a lot better to work with, so chemists, especially organic chemists, tend to prefer like bromine. Notice now it is a liquid, so it is still a fuming, angry liquid. It mentions that volatile. It's really fuming and angry, but you can still kind of transfer it over, and then it'll be angry and have all this brown, red fumes potentially that come out. And then iodine is, again, also great to work with. So I think iodine is so beautiful. Might be one of my favorite compounds, just look-wise. I don't know why. It's just so pretty. It's like purpley, shiny, and then obviously it turns into that brownish, orangish solution. And so the problem with iodine is it is a regulated substance because you can make meth. Shocking. You can make meth by a lot of routes, though, so saying you can make meth is not the greatest shock. Meth is easy to make. So there's iodine, and again, right, used a lot in chemical synthesis as well. And then, of course, don't forget to get your iodine, right? You want to, at least on occasion, use some of that iodized salt, which just means I think they use potassium iodide in there as well, right? A little bit of filler, so it's good. It protects your thyroid. And then this is obviously going to be radioactive, so not too relevant, so you won't work with that one. And then that leaves us with our noble gases. And so our noble gases, right, they tend to be unreactive. So we have helium, and then they're showing the gases in their most exciting form. So all they're doing is passing electricity through them. And obviously, because they're a gas, right, they make these nice little lamps. And we do have these at RCC, so we'll play with them during, I think, next week's lab is when we'll play with them and look at their characteristic colors. And so again, not too many compounds are formed with them. So we always say they're chemically inert. And so let's put that on our periodic table. So halogens tend to be reactive, but then noble gases are not, kind of not reactive. That being said, chemists, right, are always trying to force something. So yes, there are a few neon compounds. I was trying to see if they listed any. So neon compounds are pretty rare, though. Like I said, they get forced. Then we have argon. So argon is used sometimes in glove boxes. So let me just show what a glove box is. Sometimes you see them maybe like in space stuff. These are pretty low quality. These are what I would consider low quality. this is what a more chemist glove box is. So this is for if you want to manipulate and do reactions in an air-free environment. And so usually you use nitrogen. Nitrogen is cheap. The only problem with nitrogen, and this is more kind of a fun fact for y'all. So fun fact. So nitrogen reacts with lithium to make lithium nitride, which is this, it's kind of pretty, it's this bluish compound. But, you know, that being said, if you don't want to have your compounds reacting with nitrogen, again, it's pretty rare that it reacts with nitrogen. Then you might use argon, though, in a glove box. So argon does not react with chemicals in that way, it doesn't react with lithium. And it is heavier, but it's also way more expensive, so that's why a lot of labs do not use argon unless you would absolutely have to. And let's see, I was trying to see if there are any. So right, there's a few argon compounds. Again, it's kind of easier to force as we go down. And so now let's look at krypton. So again, right, these are getting heavier and heavier in molecular weight. We'll also later think about their little onion shells, essentially. And so you can force it, so you can make some krypton fluoride compounds. I was wondering if they would show them. But again, right, mainly unreactive. So again, showing that now krypton, yeah, you can kind of force it, more diffuse orbital. So that's kind of why as we go lower, more compounds tend to exist or more easily exist. And so we'll look at xenon compounds for sure. So xenon, again, right, we still consider it fairly unreactive. But there's xenon difluoride and tetrafluoride. Just trying to see if it would show the xenon compounds. But here's one of them. And so again, it has these different fluorides. Mainly talk about xenon difluoride and xenon tetrafluoride. So again, just kind of appreciating as they get bigger, they can be forced to be reactive essentially. Again, right, chemists are always going to try to force a new bond. And then radon. So obviously radon is going to be radioactive. So again, you would not be working with this, I mean, unless radioactivity is your thing. And then down here, we don't want to forget about them, but these are lanthanides and actinide series down here. But we'll kind of revisit them. And these aren't, I don't know, I always feel like they're kind of a disappointment. They're not maybe as exciting as maybe they should be for being down here. A lot of them kind of behave pretty simply in a lot of ways. I think they are trying to do molecular magnets, though, with some of these, like neodymium. So there is some cool research. And then obviously down here, they're going to be synthetic. And again, you can appreciate why they have funny names from their origin and people fighting to name them. And then again, right, look at the back periodic table is already outdated. And I don't even know if this is outdated. And so, right, they're trying to name these. And like I said, maybe in the future we'll have 119 and 120 for elements. All right, so that was just kind of our overview of just kind of our flavor of the periodic table. And then where we're going, so we'll probably save this for Wednesday, but then we want to start looking kind of at the electronic structure. And so we will start getting into chapter 3 just a little bit, just because of how I like to teach it, because we kind of want to understand it all together of like the Lewis dot structure, the valence electrons, and kind of how it all builds. So there'll be a lot going on on Wednesday, but then we'll kind of continue it on to the next week. All right, so that's probably, like I said, a good stopping place. Ask me questions, especially if you had any issues with the ions and the isotopes. So that's kind of the main math. And then again, interpreting these structures. And then, like I said, we'll continue on Wednesday just trying to pair together, what we saw. Okay, the alkali metals are reactive, but then how does that pair with the electronic structures? So trying to dive into that. All right, and then I'll see you Wednesday at 9 for lab. So this one should be a relatively safe one. And then remember, next week is the fire one. So just keep that in mind when you're thinking about your clothing. All right, see you on Wednesday then. Again, just ask me questions. Don't forget your homework if you have that for me. Otherwise, I don't mind if it's late. You can hand it to me on Wednesday. And then any questions online before I stop the stream?